All right, so let's start with number 1. Okay, so it says consider the curve given by x squared minus xy plus y squared equals 4. Find the 2 points on the curve at x equals 0. So we want to find order pairs. We have x values, so there's no calculus involved here. We're just going to plug in and find the order pairs. Okay, so we'll plug 0 in, see what happens. So it looks like all the zeros drops out. We're left with y squared equals 4. Take the square root. Plus or minus. Okay. It says find 2 points. Well, this is the result with just one x value of 0. So we have 2 order pairs. Oh, sorry. Okay, so plugged in 0 in for all the x's. Okay, so 2 points are 0, 2, and 0, negative 2. Okay, any questions there? Okay, part B, find the derivative by differentiating implicitly. Even if the direction didn't say implicitly, we should be able to look at this problem and recognize this is implicit differentiation. You see y's mixed into the equation, doesn't look like a normal function, right? And there's something else. What else is needed besides implicit? Product rule, yeah, that xy, right? It doesn't seem like like something that it doesn't announce itself, right? That xy we have to kind of look for, we have to be able to recognize it, that this is something we have to do an extended rule for, product rule there. Okay. Okay, so we'll start with our rule here. Oh, and then something that I want to watch out for is the fact that there's a minus sign here. I like to put that xy in a set of parentheses because otherwise I feel like I may forget about distributing that negative through when I'm done with product rule. Okay, so x squared becomes 2x. Save space for product rule here. Okay, so f prime g, x becomes 1, we keep the y plus f g prime, oops, sorry, f g prime. So x times y's derivative. Y's derivative is 1. Don't forget, there's still also a dy dx that's resulting from y's derivative. Okay, we're going to finish out the rest of the terms here. Y squared becomes 2y. We're asking for y's derivative, so we need that dy dx. And then 4 goes to 0. All right. The rest is doing a little bit of cleanup here. We'll distribute the negative through. We want to eventually get the x by itself. Sorry, get the dy dx by itself. So I'm going to leave these two terms on the left side. I'll move the other terms to the right. The order doesn't matter. You can say negative 2x plus y. Okay. Factor out the dy dx. And then finally, divide the parentheses over. Okay. Any questions here? So,
what's the negative x? Why is it negative?
This part here.
Yeah, like as a when you first when you combine them.
Oh, right. Why is it negative? Well, you see that there is a negative sign here. That negative has to distribute through the result of product rule. So when product rule comes out, there's going to be a plus in between, because now there's two separate terms. So the minus in front, we got to distribute to both terms. Yeah, that's why I like having a parentheses here. That way we can make sure we don't forget about that negative there. Good. Any other questions? Now, this dy dx, it looks like, complicated mess, but it does the same thing as other derivatives, right? You give it x and you give it information. In return, it'll give you a number, and that number is going to tell you the exact steepness of a point on this graph. So don't let the messiness of the derivative, cause you to lose focus of what it does, right? It does the same things as other derivatives. Just tells us slope information. Okay, so part C. Use dy dx to find the slope of the lines, right? So here it is, right? We know that our derivative is going to help us find the slope to the curve at the point found in part A. So we have the ordered pairs in part A. We're going to insert the ordered pairs into the derivative, and we should get slopes that are specific for each point, right? Each point will have its own slope, most likely that these are not going to be the same. So we'll see. It's possible that they are. We'll see what happens. So let's try 0, 2 first. I want to plug 0, 2 into the derivative, and typically when I want to find the slope and it's in this form with x's and y's, we like to use this notation to indicate it's basically the same thing as like saying f prime of 2, but because we need both the x and y value, we use this notation to indicate I need both the x and y value into the derivative to get my slope. Okay, so 0 in for x, 2 in for y. Okay, 2 over 4, which is 1/2. So that's one slope. We know that whatever the graph looks like at the order pair 0, 2, the graph is going to have a slight steepness, positive slope of 1/2. Okay. The other point is at 0, -2. Okay. Same thing, same derivative, same slope formula. So it looks like I'm getting the same slope, but it's different points. It just happen to have the same slope. So at 0, -2, there's a slope of 1/2. At 0, -2, there's also a slope of 1/2, but it's just coincidence. Well, there's no way for us to know unless we are actually trying to find it. I've got handouts there if you want to. Whatnot. Okay. Oh, sorry, it's on the chair there. There, yeah. Okay, write the equations of the lines. So tangent line equation means we're going to go through y minus y1. So I'm going to write a tangent line equation for this piece of information, this order pair and this slope. And then I'm also going to write a tangent line equation for this. Okay, questions so far? Part E says set up and write equations. Okay, we're not going to solve this, but how would we go about finding vertical and horizontal tangents? Right, of the derivative, right? Yeah. Of the derivative, good. So the numerator of the derivative, we set that equal to 0. That's going to give us information where the graph has a horizontal tangent line. So if the graph looks strange like this, setting the numerator equal to 0 is going to tell us where slope 0 is going to be. And if I set the denominator equal to 0, that's going to give me vertical tangents. Or more generically, it's going to give us where slope is undefined. So this is a potential place where slope is undefined. Okay, if we were to go through this process, we would solve for y, plug it back into the original equation. There's a lot of algebraic steps involved there potentially with the messiness, but for this problem, I just want us to set it up. Do you know where to look to find it if you were to find it? Okay. Vertical tangents. Okay. Any questions with number 1? Let's go to. Right. So anytime that I want to look for a horizontal tangent, meaning visually where a slope is 0, it's going to have to come from the numerator of the derivative. So I can set the numerator derivative to 0. But anytime I want to look for a place where the slope is undefined, such as a vertical tangent, I have to look at the denominator of the derivative and set that equal to 0.
Are we going to have to solve it on this?
You may have to, but I will give it to you where you can just solve. It'll be like with one variable, like 2x plus 3 equals 0. Then you can solve for x. But I won't give it to you where there's 2 variables, because that's just too much algebraic step for that I want you to work with right now. Okay. Next page. If G is differentiable everywhere, find A and B. So we talked about this yesterday, right? We talked about this yesterday, how it says differentiable, but really we want to think of, there's really 2 things going on here, right? It's what and differentiable. Continuous and differentiable. We don't have to use the word continuous to assume it, because if it's differentiable, if it's a smooth curve, then it has to be continuous. But it's nice to have those 2 distinct properties, continuous and differentiable. The fact that it's continuous means that we know these 2 graphs will connect at the same y value when x equals -2. Okay. So the fact that it's continuous means that our graphs will share the same y value. Okay. What that means is we can set the 2 equations or 2 graphs equal to each other. Because we have to create a situation where these 2 graphs connect. The differentiable portion tells us that these 2 graphs will not only connect, but they will connect in a way where there's a smooth transition in its in the graph. So there's not going to be a sudden jerky slope change from one graph to the next. It's going to be a smooth transition. What that means is that they will also share the same slope. Okay, so if they share the same slope, that means we can set the two what equal to each other. We're definitely going to set the two equations equal to each other, but we're also going to set the two derivatives equal. Okay. Okay. And the reason why we need to create two equations is because we have two missing values. Two missing values. If we only relied on just one equation, we're going to be able to get something, but we're not going to be able to solve for both A and B. Okay, I'm running out of room here, so I'm going to put this here. So the continuous portion here. Set them equal. Okay, we're not going to be able to solve for A and B, but we can at least make some progress. We can go as far as we can and clean this up. What would your next step be? Yeah, before we do any rearranging, let's make this a little bit easier, right? We're trying to solve for A and B, but what can we try to get rid of or replace? X is -2, right? Let's get the x's down to numeric values, then we can at least, so we don't have to stare at all these, these missing variables and values, right? Let's get that -2 out of the way. Okay, so this is as far as we can go. We'll leave this here. We can't solve for A. We can't go any further. I mean, we can, but we're not going to be able to solve for A or B. So we'll come back to that. The second, yes. Let's see. Oh, yeah, that's all right. Yeah, should be -2A. -2A plus B. Okay, so then next we want to involve the derivatives. So let's find the derivative for g of x, and then we can set those two parts equal. All right, so let's do this here. Let's create a derivative for this piecewise function. All right, let's do each term. What does 6x cubed minus 8x squared turn into? Minus. Sorry, okay, should be just less than. Okay, all right, let's do the derivative for this one here. Ax plus b, what does ax plus b turn into? Just a, right? This is a linear expression, so if I find a derivative, the x drops out, but everything in front we keep. The b is a constant, b is not a variable, b doesn't go to 1, b goes to 0, so just a.
So do we just assume that b is always a constant?
Yes, yeah. And I should have specified that here Yeah, find A and B, which are constants.
Okay.
Mhm. We know we can force the situation to set the derivatives equal because they're telling us it's differentiable, so we know that they must share the same slope at this -2. Okay, what would you do next? Yeah, replace the x with -2. Okay, now these numbers are kind of large here. No calculators on the test, but I'll give you easier numbers to work with on the test. And now you have your A value, you can plug in to find your B. Okay, that's not difficult, but then you gotta multiply and add. Just want to let you know though that on the AP exam, if you're dealing with large numbers as free response, you can leave your answer unsimplified and they'll give you full credit. You don't have to clean everything up. So just to let you know. So same thing on any test. If you have your answer, but it's unsimplified, you'll get full credit. All right, any questions with 2?
Wouldn't the -72 be positive?
Well, yeah, so what I did was I kind of rearranged it. I left the B on the right side and I added,
Oh, I see.
and then I flip-flopped. So sorry, I just did some rearranging. And but yeah, I can add the 2 + 1 to 4 to the right side, and that is equal to B. I set B on the left. All right, no questions with 2? All right, number 3. We have a graph in front of us here. It says h of x equals f of x times g of x. Find h prime of 2. Before we can find h prime of 2, we first have to find what? Meaning that do we deal with the 2 at the beginning? Okay, so I guess, yeah. So first, what I want you to recognize is that we don't work in the 2 yet, right? First, find h prime of x, right? We need to find the derivative function before we can evaluate it. So this is at least a 2-step process. I think sometimes students want to plug in the 2 and then find the derivative, and it just messes everything up. So focus your attention on finding h prime first. Okay, so like you said, this is product rule because of the way that this problem is set up. F prime g plus f g prime. Now what can we do? Now that I have the derivative, what's next? Now I can involve the 2, right? So 2 goes in for all the x's. All right, so now we go to our graph. F prime of 2 is asking for the slope of the f graph at 2. G of 2 and f of 2 is asking for the y values of the f and g graph at 2. Okay. Let me highlight those points there. G graph is on its way up. F graph is on its way down. Okay, so what's f prime of 2? What's the slope of this f graph at 2? -1, right? I pick another point. It's a nice straight line. So like, as long as I can identify 2 points and do rise over 1, I can get the slope. So down 1 over 1. This is the slope of -1. Okay, G of 2. G of 2 is asking for the y value of the G graph. You see that the y value there is 2. F of 2, it just happens to be an intersecting point, so it's going to share the same y value, right? F of 2 is also 2. Okay, G prime of 2, we're asking for the slope of the G graph at 2, the slope of the dotted line here. I pick 2 points that I can find, up 1 over 1, rise over 1, slope of 1. H prime of 2, I just merge those values together. -2 plus 2 is 0. Okay, questions there? Part B, W of x equals f of g of x. What does this look like to you if we want to find the derivative? What rule? Chain rule. So chain rule says outside function's derivative, in this case is f, times the inside function's derivative, which is g. Okay. Once we have our derivative, we can start working in our exact value. Okay, f prime of g of 3 times g prime of 3. What would you do next? We want to start replacing things and get it down to a numeric value. Where would you start? Okay, g prime 3, okay, we can definitely do that. That is a standalone term. We can definitely find that value. What about here, though? What would you start with this messiness? Yeah, let's find g of 3. So when you find g of 3, you're going to get a y value. That y value is going to replace this entire thing here. Okay, it's going to give us the y value for this entire notation. Okay, so g of 3. Let's go to g of 3. So g of 3 is the dotted line. It looks like what? A y value of 2.5, right? 2.5. Okay, so g of 3 was 2.5. So we insert 2.5 in for g of 3, but I'm just going to rewrite this problem here. I want this to look a little cleaner. Okay, so I'm going to wait to find g prime of 3. I just want this problem to look a little cleaner here so it doesn't look as messy as before. So now, let's take a step back. All we need to find now is to find f prime of 2.5, which is the slope of the f graph at 2.5, and then the slope of the g graph at 3. So we want the slope of the f graph at 2.5. That looks kind of messy with that decimal there, but 2.5 is here. It's part of this line, right? So we don't have to worry, we don't have to really deal with the decimal. We can just pick any random point along this line and find the slope. In fact, we already know what the slope of this line is, right? What's the slope of this line? -1, right? So it doesn't matter if it's 2.5 or 2.8 or 2.96. The slope is all going to be the same along this line, -1. Okay, g prime of 3. Asking for the slope of the g graph at 3. That's along this dotted line. What does that slope look like to you? 0. Mm-hmm.
Do you ever have a question that asks like where the slope changes?
Oh, you mean like here at these sharp turns? Yes. So if something is involving f prime of 3 or g prime of 2.5, what can we say? What's the derivative at these points? Undefined. So usually if undefined shows up anywhere in your process, it's going to wipe everything out to be undefined as well.
Okay.
Yeah. So if you have like undefined plus 1, that's still undefined.
Okay.
Yeah. Okay, part C. Z of x equals 2f of x cubed. This is also chain rule, but this is kind of a mixed chain rule here. We have an outside and inside function that we can actually work with because there's actually a power rule that we can do here. So imagine this was like 2 with messiness inside cubed. You would recognize this as chain rule, right? So maybe something that is more recognizable to you. If I ask you how to find the derivative of this, you would go through chain rule, right? You would say outside derivative times inside derivative, same thing here. It's just that the f of x is going to be in function notation, but the outside we can do power rule with. Okay, so let's identify this as chain rule. So we can actually do this outside inside identification here. Okay, what's the outside portion of this function here? 2 bracket 2. Okay. What's the inside portion? F of x. Okay, so we're just going to take turns with each derivative. Now, the reason that we're doing this for this C problem, but not for B, is because B is everything is in function notation, so we kind of have to rely on the defined form for chain rule. But here, this is kind of it's kind of like a real problem with function notation, so that's why we're able to go through this process. Okay, outside derivative first. What's outside derivative? Power rule, right? We do power rule here. And what do we insert in this space? Do we put f prime in here? What happens with chain rule here? When we take outside derivative, what do we do with the space? You put the same. You put the same function in, because we're not ready for the inside derivative just yet. We're not ready until we get to a space outside of it. Now that we have inside functions derivative, we're ready for, now that we have outside functions derivative, we're ready for inside. Inside is going to be in a separate area. It's not going to be inside this portion, it'll be out here. So what's inside's derivative? F prime. Okay. Replace every x with 0. Let's find f of 0. Let's find f prime of 0. We can insert them in, and then we can get it down to numeric value. Okay, so f of 0. F of 0, we go to our f graph. That's a y value of 4. F prime of 0 is asking for the slope of the f graph at 0. This is all part of the same part of the f graph, right? So this is what, slope what? What's, yeah, -1, right? It's -1 here, it's -1 here, it's -1 all along this line. Right. So you either leave it like this or you can clean it up, -96. D is similar to B. It's also chain rule. It's just that the outside and inside function are both the same, but I think you guys can figure that out. So I'm going to skip D and E. Well, what does E look like to you? Quotient rule, right? So you go through quotient rule, plug in 1, and the same process. Okay, so I'm going to skip these two problems. You have the key. I think you guys should be able to maybe use this as extra practice. Okay. All right, number 4. Find dy dx. This is a messy looking problem. What rule are involved here when we want to find if we want to find the derivative? Quotient rule and chain rule. Okay, and when you are deciding which rule to apply first, look at the set of parentheses. The parentheses is over most of the problem. That tells you that chain rule is going to come first. Quotient rule will follow after. Okay, so chain rule, we have to identify outside and inside. Outside is parentheses and everything else that you see outside the parentheses. Inside is what's inside the parentheses. Okay, let's take care of the outside first. This is power rule. Bring down the 7. 7 times 2 is 14. The whole set of parentheses raised to what power? 6. And we don't do anything with the inside yet, right? We're not ready for the inside's derivative yet. So we can copy all this down from the original problem. Now that we're done with the outside's derivative, ready for the inside. The inside is where quotient rule is going to happen. F prime g minus f g prime all over g squared. F prime, 15x squared. G function, no changes. Back to f. G prime, negative 2x. Okay, I'm going to put above here my cleanup of this portion here. Careful that we don't do cleanup that we're not supposed to, right? We can't take these 3 minus x squared out. We're breaking rules because this is attached to a minus. We can't cancel a cross-addition subtraction. We can't do this. We just spend the time to distribute combined like terms there. So I think this is a helpful thing to do. Split this up into 2 sets of parentheses, each with their own power of 6. I think that will help you see that denominator combined a little better. So I'm going to write this as it's the same thing, right? That 6 sees both the numerator and denominator. So I'm just starting to put all the pieces in the numerator and denominator. The result of this cleanup is going to be 45, or negative 5x to the fourth plus 45x squared minus 4x. So I distributed, combine all, I cleaned this, got rid of the parentheses. I put that up here, and I'm going to transfer this down here. Okay, any questions so far? Right, so do you see this, right, that 6, a lot of students want to just make it go to the numerator, but it's actually impacting the denominator as well. So I like to take this extra step here, because if you just look at this and try to combine these two together, a lot of students would say this is 3 minus x squared to the third power, instead of 3 minus x squared to the eighth.
On the test, say we combine like terms and 3 minus x squared to the 8th. Does that work?
Yeah, you can go from here to the 8th. I just find that taking this extra step kind of ensures that you're paying attention to that 6 in the denominator. Yeah, so I'm going to do one more step here with cleanup. I'm going to replace this denominator, merge them together, and make it 8th. Okay, particle motion, number 5. Find the velocity and acceleration function. We can go ahead and go through power rule, right? Oh, sorry. Thanks. So find velocity and acceleration. This is really 1/4 t to the 4th, right? That makes it easier to consider power rule with. And then acceleration is the second derivative, so we just do power rule twice. Find when the particle changes direction before, this is a multi-step process, right? Before we can worry about where it changed direction, we first have to figure out what? First, yeah, we need to figure out when the object is motionless, right? So we need to set velocity equal to 0. Even though it doesn't say it, it is a precondition here, right? We need that. We need to find critical points before we can decide whether it actually is going to change direction there or not. Factor out the t. I'm sorry. Normally, we would not keep -1, but the direction says for all real numbers. So that means our number line is going to span from negative to positive infinity. I'm sorry. Yeah, -1, 0, 4, yeah. Okay. Test different values with the velocity function. We'll test -2, we'll test -0.5, we'll test 1, and we'll test 5. So -2, I like to put it into the factored form and just keep track of my signs there. So that's negative, negative, negative. 3 negatives gives me negative. -1/2. So -1/2 would be negative, negative, positive. So I only have 2 negatives there. So plug 1 in. 1 is positive. 1 minus 4 is negative. 1 plus 1 is positive. There's only 1 negative. Plug in 5. 5 is positive. 5 minus 4 is positive. 5 plus 1 is positive. All positives. So what would you say? How many times does this object change directions? So at -1, it changes direction because it goes from negative to positive. At 0, changes direction because it goes from positive to negative. And at 4, changes direction because it goes from negative to positive. Okay. Guys, I didn't get through the rest of the sheet, but I have a video on the website that goes through the rest of it, so you guys can work through it. but I'll also be available tomorrow morning.